So this is chapter 24, magnetism. So magnetic fields and magnetic forces. This is an important subject on its own, but we're also going to use this subject in a future chapter when we talk about induction. So it's important. Okay, so here's the learning objectives. It's kind of a lot. Understand that magnetic fields are produced by permanent magnets. We're not going to talk a lot about that. More importantly, by currents, the movement of electric charge. Sketch magnetic field diagrams due to configurations of magnets and current-carrying wires. Compute the magnetic field strength and direction for a straight current-carrying wire, a current loop, and a solenoid. So there are three things: wire, a straight wire, a current loop, a circular wire, and then something called a solenoid, which is like a spring. Determine the direction and magnitude of the force on a charged particle moving in a magnetic field, and understand the physics of the circular motion of such charges. Calculate the force on a current-carrying wire in a magnetic field. Understand that the basic unit of magnetism is the dipole, and that dipoles experience a torque, Physics 105, in a uniform magnetic field. Okay, so first of all, let's compare electricity with magnetism. By the way, whenever I talk about electricity, I'll talk about the electric field. As before, that's the electric field. Magnetic field is B. So if I say E field, it's electric field. If I say B field, it's the magnetic field. All right, so let's compare these two. So with electricity, we have plus and minus charges. And as you know, like charges repel, unlike charges attract. With magnetism, we don't have plus and minus charges, we have poles. So we have north and south poles. And as you know from experience, like poles repel, unlike poles attract. So it's very similar, to the plus and minus charges. But there's a huge difference in magnetism. So here, let's say we have a magnet. Call this a bar magnet. North pole and south pole. Let's say we cut it in half. And so we just look at that thing. Okay, the question is, or this thing, I don't care, let's look at both. The question is, will we get just the north? Will we get just the south? And even if I keep cutting this and cutting it and cutting it and cutting it until I can't stop cutting it, will I ever get just the south pole and just the north pole? The answer is no. Okay, the answer is no. And so that's different, right? Because with electricity, we have electrons. It has a negative charge. We have protons. It has a positive charge. As far as we know in magnetism, we'll never have just a north or a south. So what we say with magnetism, we have no such thing as a magnetic monopole. So that's kind of a big deal, all right? So mono, means one. So there's no such thing, as far as we know, as a magnetic one pole. We're never going to get just north. We're never just going to get a south. However, there are people working on particle physics theories that predict that these things actually exist. So there are many experiments going on in the world today searching for these magnetic monopoles. But like I say, no evidence yet that we have it, except for this. Well, so in 1982, there was a guy at Stanford, and he published a paper, and he said that he found an event. In other words, he found evidence of a magnetic monopole. But when they repeated the experiment over and over and over again, they never found it. So basically, this paper has been discredited. But again, hey, people are still looking for these things. So don't be totally shocked if one of these days you read in the newspaper that, that they found a magnetic monopole. Okay, so this is the basic unit of magnetism. is called a magnetic dipole. Di means two, right? Magnetic dipole. So just a bar magnet. So you have your south pole and you have a north pole. And what you need to remember is the direction of the field lines. So you remember with electricity, if we had a plus charge, the E field lines pointed away. If we had a minus, the E field lines pointed towards the minus. Well, what's the deal with the magnetic dipole? So the lines point away from the north into the south. And these are actually closed loops, okay? These are all closed loops, right? So that's what you're going to remember. Away from the north into the south. We're going to use that a lot, so careful. All right, here's a question for you. Which one of the following must be at Earth's northern end? So please pause your video and analyze it, right? Don't just go by what somebody's told you. Analyze it. Just use what we've just learned. Okay. A south magnetic pole. Now, most people don't know that, right? Most people are really surprised. Okay? Most people are super surprised. And why is that? Well, here's a compass. A compass has your little needle thing here, right? And this is a north magnetic pole, and this is a south magnetic pole. So when you use a compass, where does it point? It points towards the north pole, right? Well, remember, unlike poles attract. So if this north points to this, it means that this must be a south magnetic pole. So that's kind of interesting, right? So the geographic North Pole, you know, where Santa Claus lives, is actually a south magnetic pole. The geographic South Pole, you know, Antarctica and all that, is actually a north magnetic pole. And notice they're not exactly lined up, right? So there's the north geographic pole, here's the south magnetic pole. In fact, the Earth's magnetism, the direction changes ever so slightly all the time. So there you go. All right. Back to electricity. What creates an electric field? Well, a charged particle, right? It can be moving, it can be stationary, we don't care. As long as you have a charged particle, you're going to get an electric field. So what we want to do now is ask ourselves, what produces a magnetic field? What produces a magnetic field? So we're going to do a little demonstration. So this is a power supply. Think of it as a battery. And there's a current. Well, sorry, there's a wire. It leads to these light bulbs. Then the wire goes like here and back. And there's a compass right there. So right now, I don't have this turned on. And, you know, this is just lined up with Earth's magnetic field. All right? So there's no current. You can see there's no current because the light bulbs aren't lit. So now what I'm going to do, I'm going to turn it on. You'll see the light bulbs being lit. And let's see if something happens to the compass. All right, so when we had a current moving through the wires, it produced a magnetic field. So that's the important thing. I mean, you know, there were electrons in the wire before I turned on the power supply, but they weren't moving, and they did not produce a magnetic field. It's only when I turn on the power supply to get a current, in other words, to get moving charge, that a magnetic field was produced. So that's a big difference between electricity and magnetism. Electricity, stationary charges produces an E field, moving charges produces an E field. But with magnetism, only moving charge produces a B field, moving charge only. Okay, so here's some really neat pictures. So this is supposed to be a wire, or there's a current going through this wire, right? And I don't know if you can see it really well, but look at the direction of the magnetic field lines, circles. Here's a better picture. So the current is going this way, and the magnetic field lines go like that. So it's very different than electricity, right? Very, very different. But it's all right. Okay, so here's another picture. So these are just little tiny pieces of iron. And there's a current going through this rod. And you can see that the magnetic field lines, again, perpendicular to the rod, circles. Okay, now, sorry to say this, but there's quite a few formulas in this chapter. And in order to derive them, you need calculus, but this is not a calculus physics class, so I'm just going to give them to you, sorry. All right? So, I mean, there's not a ton of them, but the ones that we'll see, you're going to use. This chapter, following chapters. Okay, so this is just a straight wire. And the magnetic field produced by the current, in other words, the moving charge in this straight wire, is mu naught. That's just a constant. Remember, we had epsilon naught with electricity. Well, this is mu naught, just a constant. Don't worry about it with magnetism. So mu naught is the current divided by 2 pi r. R is the radial distance from the wire. So let's just say that the wire, that's the wire. So it's sticking, it's perpendicular to the board. So r would be the distance, this is r, right? The distance between the wire and where you want to measure the magnetic field. Okay, so you want to memorize that. Sorry. Okay, so mu naught I over 2 pi r. And again, what we just saw, it's the current that produces the magnetic field. And you see that, right? The magnetic field equals all this stuff, but I mean, it's proportional to the current. And the further you get away, it gets smaller and smaller and smaller. Okay, now you have to know the direction of the magnetic field. You'll see that this chapter and next chapter. And we have a lot of things called right-hand rules. And there's more than one. And so you got to learn them. And if you're a lefty, I'm sorry, but you got to use your right hand. So here, all right, so this is how you figure out the direction. So pretend this is a wire or a rod or something. And let's say the current is going up. So to figure out the direction of the magnetic field lines, you grab the wire or the rod with your right hand. You make sure your thumb is pointing up in the direction of the current. Again, it's conventional current, right? And then the fingers, you curl your fingers around the wire or the rod, and that's the direction of the field lines. So in other words, they're like this, right? They're not like this, all right? That's why you got to do it with the right hand. So again, grab it, right hand, thumb in the direction of the current, curl your fingers around, and just like it shows, right? The field lines, circles, perpendicular to this thing. Okay, so you got to know that, right? Right hand rule for a straight wire. Grab it, right hand, thumb in the direction of the current. All right, okay, nice. Now, this is a little review when we talked about electricity. So we talked about something called an electric dipole. So water is an example of an electric dipole. Remember, H, so there's 2 hydrogens and 1 oxygen. So you have positive nucleus, positive nucleus, positive nucleus. So this is kind of like the positive side of the molecule. This is the negative side of the molecule. Now, in physics, we like to make models that work with like any kind of a polarized molecule. So this is our model. So we have a plus end and a minus end. By the way, for you medical types, the human heart acts like an electric dipole. So you're actually going to use this stuff maybe if you're a physician, All right, now, electric dipoles. Well, we want to talk about magnetic dipoles, right? Okay, we already talked about it. This is a magnetic dipole, right? We have a north and a south. Field lines away from the north, into the south. Now, here's the question. How do we make such a thing? I mean, how do you make a bar with a wire? How do you make a magnetic dipole? So here's a circular wire, and let's say there's a current going like this. Okay, so just use that right-hand rule. Grab the current, grab the wire with your right hand. The thumb is in the direction of the current, and the field lines follow the direction of the fingers, right? So they kind of go like this, you know? Just pretend circles. So look at, underneath this, okay, so here's a plane, right? So underneath this plane, the field line's coming up, and above the plane, the field lines go up. So what does that look like? I mean, think about it. Let's say it's like this, right? The field lines go this way here, that way here. So in other words, if you have a current going through a circular wire, you have these magnetic field lines, right? And they all go on the top here, they all go up. On the bottom here, they all go up. So what does this create? This creates a magnetic dipole. So, all right, so here, again, look. So here's the here's the wire. You have the current going this way. You just grab it, right? You grab it with the right hand, so your thumb points in the direction of the eye. Then you have these circles. So where does it point? It points as shown, right? So, hey, how do you make a magnetic dipole if you don't have a permanent magnet? You just put a current in a circular piece of wire. So maybe this will help. I don't know. So here's your circular wire. Currents in that direction. Right-hand rule, and you can see that on top field lines go up. On the bottom, field lines go up. Right. So it's exactly the same thing as a bar magnet. Right. North, south, because on the top of the plane formed by the circular wire, up, and the bottom up. And they form these closed loops, okay? So there you go. So you can either have a permanent magnet, you know, that has like this, right? Just this thing here, a north and a south, or you can produce that with a circular piece of wire as long as you have a current going in it, right? Okay, so that's kind of a big deal, all right? So that's what you want to remember, right? A circular current loop, just a wire with a current going through it, you know, a circular piece of wire with a current going through it, produces a magnetic dipole, just like a permanent magnet, you know, is a magnetic dipole. All right, so you'll see that sometimes we would like to know what the B field is at the center of the circular wire. So, you know, here's the circular wire. We want to know what you'll see why. We want to see what the B field is right at the center here. And using calculus, you can figure out the answer. So the answer is mu naught. Yeah, you're always going to have this mu naught with magnetism. So mu naught I, I'll get to that in a minute, over 2r. So it's similar to the straight wire, right? Now, uppercase N. Uppercase N in this chapter is always going to be the number of loops, right? So let's just say you had, just one piece of wire. Then uppercase N would be 1. Now let's say I had a really, really, really long piece of wire, and you just kept wrapping it, you know? So the book says it's like the number of turns, but it's one long wire. You just keep wrapping it, okay? All right, so there. So the B field at the center is mu naught, number of turns, current, divided by 2r. Okay, now let's see. So this is just a slinky, right? So pretend this is metal. So pretend this is just a really, really long wire that's made into this form, okay? So let's just take one loop of wire, right? And so, just look at this one loop of wire and put a current in it, and you're going to get these magnetic fields, right? Circular, 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 right? But now, let's say we go like this. Not the greatest, but I hope you understand. So that's called a solenoid, right? A solenoid. Just like a slinky and just connect it. Now, I mean, think about it. What's the B field going to look like? You know, you have the B making circles around every single circular loop, right? So what is that B field going to look like? Okay, so there's the solenoid. Just pretend it's, oh wait, it's not supposed to be connected. Gosh, forget what I just said. This is the solenoid. I was talking about, this is a toroid. We're not going to talk about a toroid in this class. Sorry. This is the solenoid. You don't connect it. All right? So the solenoid is just that. Just a spring. It's easy, right? Okay. Now this picture is kind of hard to interpret. You've got to really think about it. So remember, the X means that the current's going in, and just a circle means that the current's going out. Remember, this is supposed to be the feathers of the arrow going in, and this is the arrowhead going out. And so you can see, right-hand rule, grab that wire, right hand, right? So the current's going in this direction, so you get all these circles, right? Get all these circles. So you get all these circles from every turn of wire. And look, they're all going, you know, inside the solenoid, they're all going to the right. So basically, inside the solenoid, you get this really large magnetic field going to the right, because every single one of these wire turns or wire loops, you know, produces a magnetic field inside going to the right. And outside, it's just a little, it's much, much less than inside. And so what we're going to do, because we like to make life easy, we're going to just ignore the magnetic field outside, because it's really super small compared to the magnetic field inside. Right? So ideal solenoid, we just ignore this outside, and we just have this super, super strong magnetic field inside. And here's the equation. Wow, 3 equations already. Magnetic field inside a solenoid, mu naught, looks familiar. N, looks familiar. I, looks familiar, divided by L. What's L? L is just the length of the solenoid. Just the length. Okay? So we're going to use those. If you don't want to memorize them, just have them handy when you're doing your homework. Okay, so look at this. Is there any kind of a pattern here? The B field for a straight wire, mu naught I, 2 pi r. The B field inside in the center of the coil, mu naught Ni over 2r. The B field inside a solenoid, mu naught Ni over L. So what's the pattern? Well, I hope you understand that, you know, I mean, here you can say N, you can put an N here, but N is 1, it's only a single wire, right? So the numerator is always mu naught Ni. Mu naught Ni. And the denominator is always some kind of a length. So that's the pattern for these 3, right? B field, mu naught Ni over L. So if we want to, so of course, the B field is proportional to the current. Larger the current, larger the B field. Okay, I want to show you another demonstration. You can stay there. Actually, I don't even need that. Oh. Okay, so so here's a box of pins. Here's a solenoid. Now remember, I said that there's going to be a really strong magnetic field. So let's put a current on it. Let's see if it does anything. Nope. Okay. So instead of now look at it, this is just a piece of plastic, right? This is an eraser thing, you know? So instead of putting the wire around a piece of plastic, let's put it around a screw with a bolt. Now a screw with a bolt has a little bit of iron in it, right? So that's the first thing. Second of all, we're going to use something called magnet wire. See, this is just regular wire, right? Regular insulated wire. And so I really can't go to get a whole lot of turns of wire on it. But here, it's super thin. This may not look like it's insulated, but it is insulated. This is insulated magnet wire. So you just wrap it around this a whole bunch of times. So I can get much more, many more turns on this than I can on this. So let's see. Got to connect it to the battery, right, to get the current. All right? So I can see, so this is called an electromagnet. All I did is produce, it's a solenoid. And they actually use these things like in junkyards to move, to move big pieces of cars around, metal cars. All right, let's quit.